Okay, in this video we're going to look at an example of evaluating a double integral over a region R. And so we've got our example written down here and a graph of our region. So we want to use Fubini's theorem to set up this integral and then evaluate this integral. So Fubini's theorem requires that our function that is to be integrated, so in this case that's the function x over y, is continuous on our region R. And notice that this function here is not continuous when y is equal to 0. So we would want to verify that we're okay with that. So our region here, though, with our x and y axes as usual, y equals 0 would be here. And so our region doesn't include any points that have y equals 0. So we're okay with that. Our function is continuous on our region. And our region should be a closed and bounded region in R2. So we have a closed region, the boundary is included, and bounded, it does not go off to infinity. Okay, so we should be able to use Fubini's theorem to set up this integral and then evaluate the integral. So the first thing that we want to think about is the region, and then at the same time we also want to think a little bit about the function, whether we would prefer to integrate this function with respect to x or y. So it doesn't really matter which of those things you think about first. I tend to think about the region first. This region, I want to think about whether it is x simple, y simple, neither, or both. So I'm going to start by thinking about the region as x simple. So I want to think about if I go through this region in the direction of increasing x, am I always entering the region along the same curve and then leaving along the same curve? And I am. So if I go through this region in the direction of increasing x, we're always entering at x equals 0 along the y-axis, and then we're always leaving through this line. Even at the bottom, where it's just a single point, you're entering along the line and leaving along the slanted line, and also along the top. You enter the region when you hit this line here, and leave when you hit this other line over here. So this region is x simple. I may also want to think about whether the region is y simple. So I want to think about when I go through the region in the direction of increasing y, am I always entering and leaving along the same curves? And I am. When I go through the region in the direction of increasing y, I'm entering along the slanted line, and then I leave through that horizontal line. So it is also y simple. So this region is both, which means in terms of the region, it doesn't matter whether I integrate with respect to x first or y first. I also want to think about the function to integrate. So that is our function here, f of xy equals x over y. And I want to think about whether that function is easier to integrate with respect to x or with respect to y. So partial integration, treating the other variable as a constant. And so this is not hard to integrate with respect to x or with respect to y. One might be slightly easier than the other, but neither one of those is a very difficult integration. They both involve things you would have done at the very beginning of Calc 1. All right, so I'm going to go ahead and set this integral up both ways. Both our region and our function tell us that we can set this integral up with either dx on the inner integral or dy on the inner integral. So I'm going to set it up both ways, and then we'll talk about which ways may be a little bit easier and evaluate one of those ways. Okay, so if I do x on the inner integral, I want to think about this region in terms of it being x simple. And I want to set this integral up with dx on the inner integral. So I'm going to go ahead and write down my outer integration sign and fill in my limits of integration there later. My inner one is the one you want to start setting up first. And I'm going to be integrating the function x over y with respect to x first, and then with respect to y. So we think about this as a nested integral. You don't have to put the brackets there, but it can be helpful sometimes when you're thinking about setting these up to put those. Okay, so when you set up these limits of integration, this lower limit of integration has to do with where you enter the curve as you go through that region in the direction of increasing x. So you want to really use that picture, and I really suggest that you draw the arrows exactly like I did. So thinking about where you go through that region in the direction of increasing x, you're entering along this curve, which is at x equals 0. I'm going to write x equals 0 here. You really could just write 0. It's implied that that's an x value because you have dx here. So x equals 0. And then I need the equation where we leave. So in general, those are not all going to be constants. If your region is a rectangle, then all your limits of integration end up being constants. But remember that in general, your limits of integration are not going to be constants. So I always enter at x equals 0, but when I leave at different values of x, but they're all in terms of whatever the equation of this line is. So you might be given the equation of that line, or you might have to find the equation of that line, but either way you need to do that. When you write the equation of this line, since we're not given this, you probably think about it in terms of y equals mx plus b, thinking about slope and y-intercept, and use that to write the equation of the line. So slope is 1, up 1 over 1, or on the whole region here we've gone up 3 over 3, and the y-intercept is 1. So the equation of that line is y equals x plus 1. But remember here, if I'm doing this as a dx integral, dx on the inner integral, I need this in terms of x. So I'll need to solve this for x. X equals y minus 1. And you can write x equals. Your textbook won't write x equals on either of them. You could write x equals on both or just on one or the other. dx here indicates that these are x equals. All right, and then to set up your outer limits of integration, there are several ways to think about this, but again, I'm going to talk about this in the way I did in the last video, and what will help you when we go to three-dimensional regions that we're integrating over. Once you've set up that region in the direction of x, you want to think about collapsing that region back in the x direction. So collapse it back into the x direction and look at the projection of where that region is at on that remaining variable. When we do three-dimensional ones, we'll do the same thing, collapse it in one direction and look at the remaining variables. So I've gone in the direction of increasing x. If I collapse that back, you can see here that we would be from y equals 1 to y equals 4. So our outer limits of integration will be from y equals 1 to 4. Your outer limits of integration should always be constants. If they're not, you've done something wrong in setting that up. So if you look at that statement of Fubini's theorem again, your inner limits of integration in general are going to be functions. Your outer limits of integration will always be constants. And again, your textbook won't write y equals. dy indicates that these are y values here. So that's my integral setup with dx on the inner integral. If I want to set this up with y on the inner integral, we'll go ahead and do that here and then choose one of those two to evaluate. So I've got my outer integration sign, my inner integration sign here, my function that I'm integrating, and I want to set dy up on my inner integration. So my differential dy here, notice I put my differentials first, and then I'm going back in and filling in my limits of integration. So I'm going to go back to our original region. I'm going to think about going through the region in the direction of increasing y. When you go through that region in the direction of increasing y, you enter at y equals x plus 1. And you're going to leave at y equals 4. And then you want to think about setting up these, the remaining limits of integration. So once I've gone through that region in the direction of increasing y, I'm going to collapse it in the y direction and look at the shadow of where that region is at. And so the last one, the shadow was right where the region was on the y-axis. But notice on this one, if I collapse that thing in the y direction, I end up with a shadow down here on my x-axis going from x equals 0 to 3. X equals 0 to 3. Okay, so there I have my integral set up both ways using Fubini's theorem. Again, outer limits of integration always constants. In general, your inner limits of integration are going to be function equations. And now I need to actually do the integration. So I might think a step or two ahead, remembering that you would integrate first with respect to whatever's inside, and then eventually you're going to have to integrate with respect to whatever's on the outside. So on this one, if I integrate with respect to y, I will think about that as x times 1 over y. And the integral of 1 over y with respect to y would give me ln of y, which is not hard to do. I would then put my limits of integration in for that. But the issue is I would then have a logarithm function that I have to deal with in my next integration. That's not impossible, but maybe a little bit harder to deal with. Generally, integration involving logarithm functions, you're probably going to use integration by parts than it might be if I choose to do this one with respect to x. So I'm going to do this one with respect to x. You might try also doing the same problem with respect to y. Try to get through that integration and compare your answers. It should be the same answer at the end. Okay, so I'm going to do this one with respect to x. It turns out to be a little bit easier here. How you get good at making that decision is sometimes doing problems both ways and noticing what things about the problems make the integration a little bit difficult. Also, just like when you play chess, maybe you can think a few steps ahead and think about what's going to happen later and know, oh, this one's going to turn gross. I'd rather do the other problem if I could do it that way. Okay, so I'm going to leave off my x equals and y equals on my next steps here. Your textbook will always do that. You could certainly feel free to leave them on if it helps you keep track of things. I'm going to do the inner integral. And I'm going to go ahead and rewrite this as x times 1 over y. You don't have to write it that way, but you want to think about it that way. And now we're going to integrate with respect to x. So this 1 over y is just like a constant that's going to come along. Let me go ahead and write down my outer integral here. The 1 over y is like a constant that's just going to come along, so I'm just going to write that out front. And then the integral of x with respect to x is 1/2 x squared. So just like partial derivatives, but here it's partial integration with respect to whatever variable it's telling you to integrate with respect to. All right, and then I'm going to do from 0 to y minus 1. Those are going to go in place of x. Remember, those were x equals. All right, now I'm going to go ahead and evaluate this inner integral here. I'm keeping my notation correct here. Integral signs should not disappear in the middle of the problem and then reappear later in the problem. That's not okay to have notation like that. This 1 over 2y I'm going to put out front here. 1 over 2y, and then I'll put in y minus 1 in place of x. And I'll have the quantity squared. And then I'll put in 0 in place of x and subtract that. You might be able to see a couple steps ahead that that's going to just turn out to be 0. Okay, so at that point I have finished the inner integral. I found an antiderivative. I used fundamental theorem of calculus to evaluate that antiderivative at the two endpoints and subtracting here in functions, I guess, and subtracting here. So now I need to do that next integration. So you want to think a little bit about what simplification might be helpful. Certainly realizing that this is all just going to be 0, and so I can get rid of that is helpful. And then thinking about what I want to do with this so that I can integrate with respect to y. I would probably choose to multiply out the y minus 1, the quantity squared, and then distribute through a 1 over 2y, or maybe pull the 1/2 out front and distribute through a 1 over y. I'm going to skip just a little bit of that algebra here just so that we have room to finish this example. So we'll have the integral from 1 to 4. And then when I square this out, I'll have y squared for my first term, and then that will be over 2y. So y squared over 2y will reduce to y over 2, right? The y squared and the y in the denominator, the y squared in the numerator and the y in the denominator, one of them will cancel. The middle term here will be minus 2y, and then when I have that over 2y, I will just have a minus 1. And then the last term here will be 1 plus 1, and then I'll have that over 2y. So plus 1 over 2y. All right, so I just did the algebra there of expanding out y minus 1, the quantity squared, and distributing through a 1 over 2y to each term. So the reason that's helpful then is that these are then all basic antiderivatives that you should know from Calc 1. So you just do your integration here. So for this first one, I've got 1/2 times 1/2 y squared. So I get 1/4 y squared. Here I'll have minus y. And then here I'll have plus 1/2 times natural log, technically of absolute value of y. So I'll think about that as 1/2 times 1 over y to do that. You can get away with neglecting the absolute values on this one since the values that we'll be plugging in are always positive. And now I need to just evaluate that from 1 to 4. So I'll put in 4, I'll put in 1, subtract my answers. So from here, actually from about here, it's really a Calc 1 problem. So that's why we reviewed all that stuff in week 1. All right, so let's see. When I put in the 4, I'll have 1/4 times 16. So 4 minus 4 plus 1/2 ln of 4. And then when I put in 1, I'll have 1/4 minus 1 plus 1/2 ln of 1. ln of 1 is 0. And at that point, I actually have my answer. It's just a matter of tidying it up. These two add up to 0 as well. So let's see. It looks like I have here 1/2 times natural log of 4. And then when I combine these, I get negative 3/4. And then minus negative 3/4 will be plus 3/4. All right, so there is my answer. And again, if you do the integration with dy on the inner integral, you'll notice that your integration is a little messier. You have to use some integration by parts in there. Maybe a u substitution as well. Here, all I had to do was really just some algebra. But you should end up with the same answer at the end. So there's a little challenge problem for you. If you want to try your integration skills, try that and see if you can get to the same answer at the end. In general, though, on a test, you probably want to choose the easier way through the problem so you don't get bogged down in some messy integration. All right, we'll look at some more examples, kind of an increasing level of difficulty where the setup is maybe a little bit tricky and or the integration in the middle is a little bit tricky.